Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the ionization energy of an electron from potassium. So let's get into this. So in this problem we're told that a technique called photoelectric spectroscopy is used to measure the ionization energy of atoms. A sample is irradiated with a UV light and the electrons are ejected from the valence shell. The kinetic energy of the ejected electron is then measured. Since the energy of the UV photons and the kinetic energy of the ejected electron are known, we can write this equation here. This is Planck's constant multiplied by nu, the Greek symbol nu, which stands for the frequency of the light or the photon, is equal to the ionization energy of the electron that's ejected plus the kinetic energy, 1/2 mass times v squared. So this is the mass of the electron multiplied by the velocity of the electron squared. So this is your kinetic energy. And so they're saying in one experiment, the kinetic energy of the ejected electron from the potassium is found to be 5.34 times 10 to the negative joules using a UV source of 162 nanometers. And then they want us to calculate the ionization energy of potassium. And then they ask a question, how can you be sure that this ionization energy corresponds to the electron in the valence shell, that is the most loosely held electron? So we're going to answer both those questions. But first we need to calculate the ionization energy of potassium using the information they give us. So here we're going to use this equation. So the first thing we need to do is calculate nu. What is the what do you call it? The frequency of the photon. So they give us the nanometers. They give us the wavelength of the photon. So we're going to need to use this equation. So we know that C is equal to nu lambda, right? So it's going to be nu times lambda, right? Or you could see that lambda is going to be equal to, or nu, or lambda we want to use. So we have lambda. Lambda is the wavelength, so that's the wavelength. So we have 162 nanometers. We're going to want to convert that to meters because the speed of light and velocity are in meters per second. So we're going to need to convert that to meters. So let's do that first. So 162 nanometers over 1. Nano means 10 to the negative 9, or 1 billion, or 1 billionth of a meter. So we're going to use that as a conversion factor. So I'm going to put 1 nanometer on the bottom and 10 to the negative 9 meters on top. So that's going to cancel out. And then we end up with meters. And so when we calculate this, this is going to end up being 1.62 times 10 to the negative 7 meters. Okay, the speed of light is 3.0 times 10 to the 8 meters per second. So we can plug that in. So we can solve this for frequency nu, because we want to find nu, because nu, or the frequency, is in our equation here. So we're going to have to solve this for nu. Nu is equal to C over lambda, which is going to be equal to 3.0 times 10 to the 8 meters per second over And then this is lambda in meters. So we're going to put lambda in meters. So 1.62 times 10 to the negative 7 meters. So meters are going to cancel out, leaving us with per seconds. Per seconds, or 1 over seconds, is frequency. That's the frequency unit. So then we do our calculation and we get 1.852 times 10 to the 15 per seconds. Let me double check that. 1.852 times 10 to the 15, yes, per seconds. Okay. So now that we have nu here, then we can plug that in. We know that. And then this whole thing here is equal to kinetic energy. And they gave us kinetic energy, so in joules. So we don't need to calculate that. They gave it to us. So then basically this equation is going to be H nu equal to the ionization energy plus the kinetic energy of the ejected electron. So we're going to plug in our Planck's constant, which is going to be 6.626 times 10 to the negative 19. Let me double check that. Oh, 34, negative 34. I was thinking about something else. Negative 34. Okay. And that's joules over seconds. Or, sorry, joules seconds. Getting discombobulated here. Okay. So that's our Planck's constant. And we're going to multiply that by the frequency, nu, which is what we calculated here. So that's 1.852 times 10 to the 15 per seconds. And that's going to be equal to the ionization energy plus the kinetic energy, which is 5.34 times 10 to the negative 19 joules. Okay, so now all I have to do is solve for the ionization energy. So notice that this seconds are going to cancel out with seconds. So when we multiply this, what do we get? We're going to get 1.227. So this is 1.227 times 10 to the negative 18 joules. And again, equal to IE plus 5.34 times 10 to the negative 19 joules. And then all I have to do is subtract this from both sides. So I'm going to subtract 5.34 times 10 to the negative 19 joules on this side. And I'm going to subtract 5.34 times 10 to the negative 19 joules on this side. So this cancels out. And so I don't need this anymore. So I'm going to erase this to give myself some room. So now I have these added together. When I add those together, I get 6.93 6.93 times 10 to the negative 19. And that's going to be joules is equal to the ionization energy. Now, we're not done yet. Be careful here, because if you just stop here, you don't have the correct answer. You're almost done. Now, the thing here is we have actually calculated here the energy that's needed to remove one valence electron. So this is the number of joules required to remove one valence electron. So this is the ionization energy of one electron. But normally, when they give you ionization energies, they give you it in terms of per mole, not per one atom, right? So this is electron that's removed from one atom, but we would like to calculate that for 1 mole of potassium atoms. So when you look up on your table the ionization energy of, say, the first electron of potassium, you're not going to get this answer. You're not going to find this, right? Because when you look it up in the table, it's not per one atom of potassium, it's per 1 mole of potassium atoms. So we need to use a conversion. So this is for one atom. We want to convert this to 1 mole of potassium atoms. So here, we have 6.93 times 10 to the negative 19 joules per 1 atom of potassium, right? But we want per 1 mole of potassium atoms. So what we got to do is use Avogadro's number. So 1 mole of potassium atoms is equal to 6.022 times 10 to the 23rd atoms of potassium. So we're going to put 6.022 times 10 to the 23rd atoms of potassium on the top, and 1 mole of potassium on the bottom. And so atoms of potassium cancel out, and we get, oops, I forgot one thing. Also, this has to be changed to kilojoules, because again, it's going to be not joules per mole, but kilojoules per mole. So we just did this step here to convert 1 atom of potassium to 1 mole of potassium. But now we have to do this. We have to change joules to kilojoules. So we'll add one more conversion factor step, and we'll convert joules to kilojoules. And the conversion factor between joules and kilojoules is, since I know kilo is 1,000, 1 kilojoule is going to be 1,000 joules. So I'm going to put 1,000 joules on the bottom and 1 kilojoule on top. So now joules cancel out. Now I have kilojoules over moles. And so when I calculate this, I get 417 kilojoules per mole. And so that is the ionization energy of potassium. So now, what about this other question? It says, can you be sure that the ionization energy that we just calculated corresponds to the electron in the valence shell? And the hint here that they're giving us is that this is the most loosely held electron. What does that mean? It means that it is the easiest to remove. It takes the least amount of energy to remove an electron from your valence shell. Why is that? Well, the reason is because it's the farthest from the nucleus. The nucleus is the positive center of the atom. That has an electrostatic force. It has an attractive force to the electrons. And the way the electrostatic force works is, according to Coulomb's law, right? Two charges of opposite charges, the attractive force is going to increase as they get closer together. The further you draw them apart, that force is going to decrease. That attractive force is going to decrease. So the farther you are from the attractive force of the positive nucleus, or the farther away you are from the positive nucleus, the attractive force is going to be weaker. And so the electrons that are farthest from the nucleus, the positive nucleus, those are the valence electrons. So they're going to be the farthest away, and therefore they're going to be the weakest. They're going to feel the weakest attractive force, and so they're going to be the easiest to remove. And so, since the ionization energy is the energy needed to remove an electron, right? Then that ionization energy is going to be is going to correspond to the weakest electrons being removed first, right? So that's what the ionization energy is referring to. So the ionization energy is the energy needed to remove an electron from the atom, right? You could remove other electrons, but the first electron that you remove from the atom has to be from the valence shell. Otherwise, it doesn't make sense. So you're not going to remove an electron that's further in towards the atom before you remove the valence electron, because again, those inner core electrons are feeling a stronger pull, and it's going to require more energy. So you would most likely remove an electron from the outer energy first, from the valence energy level first, before you remove anything else. And so that's why we can say that this ionization energy does correspond to the electron being removed from the valence shell, because it's the most loosely held on by the atom. And so that's it for this video. I hope this made sense. I hope I didn't blab on too much on that last part, but I hope it was clear. If you like this video, if you learned anything from this video, then please by all means like the video, share the video, hit that like button somewhere over here. If you if you like my channel, then please do me a solid. Subscribe to the channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any questions or problems you need help with, or a topic you would like me to cover, then put that in the comment section below so I can do that for you. Thanks for joining me, and have a great day.